Well, good afternoon, almost evening. So thanks all of you guys for sticking around. And I must confess that this is also going to be a technical talk, so just so you're prepared. So it turns out, of course, that many missions have been leveraging low thrust a lot. And up there we've got Dawn and Hayabusa, which were very successful and leveraged it in their heliocentric trajectories. Now, typically, in order to initialize such arcs, in order to design the trajectory in the first place, there's lots of different ways to do that. Sometimes with conics, sometimes with other types of models. But not very often, when you're first designing those kinds of trajectories, do you have initial guesses for the control states for the low thrust arcs. And so there's a lot of reliance on numerical methods and numerical optimization. Now that gets more complex when the missions are going to be working in multi-body regimes. So for example, upcoming Lunar Ice Cube and the Gateway PPE and the Gateway vehicle itself, they're going to be moving in the Earth-Moon space, and sometimes the Earth-Moon-Sun space. And so there's extra complexity when you're trying to design a low thrust arc for those particular mission scenarios. And so there's chaotic dynamics in there, and the solution is extremely dependent on the initial guess. And in particular, some of my colleagues that are working on Gateway, actually they use optimizers, but they typically have to cycle through, give it a lot of random initial guesses, because they get lots of different local minimums as far as the solution is concerned, and then they ultimately just pick the lowest one. And so there's a lot of time and effort that's involved. So when we were thinking about this, in particular, one of my co-authors is the main trajectory designer for Lunar Ice Cube, we wanted to step back a bit and say, not necessarily because we were trying to find better solutions or anything, we weren't challenging any of the optimization. What we wanted to do is try to get a better understanding from some fundamental analysis in why the low thrust solutions that the optimizers were producing, why they were delivering those particular types of solutions. So that's really what we were interested in and we started out to look at. Now that means that we basically, in a multi-body regime, we need to work in the circular restricted problem, or at least the restricted problem, the three-body problem. Both of the scenarios I mentioned for Lunar Ice Cube and Gateway ultimately need the four-body with three major gravity fields, but we're starting here in the three-body. And one of the reasons for that is because in the three-body, when you have a lot of ballistic arcs, you have a lot of structures that you can count on in order to gain some understanding into the dynamical environment. So you've got equilibrium points, you've got the zero velocity curves of the forbidden regions, you've got periodic orbits, you likely have invariant manifolds, or you do have invariant manifolds of different types, some being stable and unstable. And so that sort of helps you get a general idea at different types of energy levels what's going to happen. So we wanted to work at that very basic level, except add low thrust into the equations and see what would happen. See if we could look for equilibrium solutions, see if we could do some evaluation of perhaps some kind of zero velocity curves that would bound the motion, to see if we could have a better idea of why those optimized solutions were coming out the way that they were. So that's really what we started to attack. Now this is sort of the way that we organized it, and so that's the way I'm going to talk about it today. And the first thing is just to add those equations and get a restricted problem in low thrust to see what we could do with it. And it will count a lot on the energy, or we will depend a lot on the energy expression. So some of you may be familiar with this particular problem, but this is sort of a standard setup for the circular restricted three-body problem. We have our inertial coordinates, and then these are our rotating coordinates, where we've got, in our case, the Earth and the Moon, because we're interested in the cislunar type region. And we have their orientation through theta. Theta dot is a constant. And so that's typically how we set the problem up. It's parameterized by the mass ratio, which in this case would be for example, the Moon relative to the sum of the masses. Oops. So these are our differential equations, basically. They're pretty well known these days. I would also like to comment that in this particular case, there's one integral of the motion, which is the Jacobi constant, which also is a scaled version of the Hamiltonian. So that is a particular useful quantity with what we're looking at. So that natural Hamiltonian is actually just -1/2 the Jacobi, -1/2 the Jacobi constant. So we'll utilize that information. So in order to deliver a set of equations that incorporates low thrust, we just added these other terms here, which includes a low thrust acceleration in a particular direction. Now the coordinate frame that I have here is the rotating frame. So x here is the distance from the Earth to the Moon. So this angle alpha and angle beta typically will orient that thrust acceleration vector. So we also have what I'll call the low thrust Hamiltonian, which we can derive when we add those other terms, and the expression is down here. And in general, that is not an integral of the motion. So once we add the low thrust terms, we don't have the integral that we had in the ballistic problem, and we need to take that into account. But first of all, I want to ask, what kind of thrust magnitudes should we be talking about? What's realistic, and if we're going to use low thrust in this particular problem, what kind of numbers should we actually see? So what I have here is a summary with some recent vehicles. So we've got Deep Space One, Hayabusa, Dawn, and this is for Lunar Ice Cube. And so those are all those numbers and so on, but when I'm talking about the restricted problem, I need to talk about a non-dimensionalized type of mass. And so what we're going to be looking at, given all these numbers, is that basically when we get to our non-dimensional values, we're talking about e to the -2, e to the -1. So in particular, for our purposes, almost all of our acceleration level is going to be 7 times e to the -2 as a representative number that is consistent with what we're looking at now. That's actually most closely aligned with Deep Space One, but it's in the range of all of the others. So that's the low thrust acceleration that we'll be looking at. We're also going to add some other simplifications to the problem. We're going to make it planar, so the out of plane angle we're not going to have to worry about. We're also then going to be focused on this angle alpha, which is going to be the direction of the acceleration, the low thrust acceleration vector, relative to the Earth-Moon line. So you're going to see a lot of alphas. So it's always going to be the orientation of that vector relative to the Earth-Moon line. So we're going to make a few other simplifying assumptions, which is going to help us, and assumptions that we think are reasonable in our particular problem. For example, once we look at the changes in the mass on the vehicle during low thrust, for the kind of accelerations levels we're talking about, that's quite low, and the rate of change is quite low. So we're going to assume the mass is constant over the time intervals that we're interested in. And that seems reasonable in this particular problem. We're also going to assume that in the energy ranges that we're interested in looking at, we can also talk basically about a constant Hamiltonian along our low thrust arcs that will act like an integral for us. And so we've also looked at that, and that is reasonable for what we want to look at in the range that we want to look at. We're in the Earth-Moon problem, and it works very well there. It turns out that if we go to another problem, such as Sun-Earth or another type of three-body system, we can make the same assumption, we just have to sort of use different characteristic quantities. So it's reasonable for what we want to do, and those are the assumptions that we made. So we've got the low thrust Hamiltonian down here. Here is that acceleration term, and on the low thrust arcs, that's going to be generally a constant. We're also going to look at this first piece. Oops. Okay, help me out here, guys. Thank you. So I'm also going to note that at any point in time, we may also see the natural Hamiltonian, and remember that just came off of the ballistic three-body problem that's related to the Jacobi constant. So really, the extra terms that we're talking about here is where we added that acceleration. So the first thing of interest that pops in this problem is looking for equilibria. So looking for the equilibrium solutions when we're talking about a low thrust problem. So this is the ballistic problem, and anybody who works in this problem is familiar with 5 equilibrium points or the Lagrange points. True?
Yes.
Okay, thank you.
Taylor's,
Yes, absolutely right. So take note of where they are, because in this particular case, this is the Earth, this is the Moon, and those are the relative positions. So in that particular case, we're going to add, remember we have a planar problem, we're going to use the acceleration level of 7 times e to the minus 2 in our low thrust 3-body problem, and we're going to note that at any particular alpha value, we can define new equilibrium solutions. Now the other thing, it's a little hard to see here, but we've got the ballistic solutions in blue. Pretend those are blue, okay? So that's L1, L2. We've got, these are the equilibrium solutions that we're going to get for a certain alpha value. These black stars are the ballistic ones. I think a minute ago I said blue, that was incorrect. The black stars are the ballistic equilibrium solutions. Now when I use an alpha value for the low thrust acceleration, I pick up different solutions. 1 and 2 look fairly close, but now I've got an equilibrium solution here, here, and here. And you'll notice they're no longer symmetric. Shouldn't be surprising since we've added a term at an angle of 133 degrees. But the other thing that I note is that when I'm adding or putting it at an angle of 33 degrees instead of 133, 33, I've got the equilibrium solutions at 1 and 2 like they were before. These are the ballistic guys, and there's only 1 additional equilibrium point. So rather than the 5 that we have in the ballistic case, for certain angles of the acceleration vector, I end up with only 3. So looking at different acceleration levels, I can see where this occurs. So here I've got an acceleration level that is very small compared to the baseline one that we're using, which is 7 e to the minus 2. And if I look over all the alpha values, I can see where these equilibrium points shift. So this is a lot smaller than what was on the last slide, but I see these arcs because they represent, for that acceleration level, looking over all the different angles for my acceleration vector. And when the acceleration level is small, those are close to the natural solutions. As the acceleration level increases, though, we can see the range, depending on the alpha, the range of the locations expands greatly. Something is happening in here too, but it's pretty small, so we'll go back to that in a second. When we reach 7.E2, which was our baseline based on the spacecraft that we've been flying, we see that actually these 3 different types of curves have merged together. So we've got 1 and 2, but we've got a merge set for 3, and that's when we get to this acceleration level. Now you can't see it very well on this screen, but they're in different colors, and I'll come back to that in a second. So these curves are not, for example, zero velocity curves or anything. They're just the collection of equilibrium locations for every different type of alpha value. If I start to grow the acceleration level even further, the one on the left there is our reference acceleration level. This one is larger. We can see that they start to reach the moon region as well. These curves, which we call, actually I had that in the last slide, we're actually calling these zero acceleration contours, but it doesn't matter what you call them. But in this particular case, we call the contours E1, 2, and 3, which is especially relevant once they have merged. And if we get to larger and larger values of the acceleration level, you can see what happens to the curves. so that you can also see where the equilibrium solutions are moving when we're starting to talk about higher acceleration levels. This is a little bit hard to see, but this actually collects all that information. And in doing so, we've got at the acceleration levels that is completely ballistic. You have the 5 equilibrium points that are at the peaks of these guys here. They're actually blue. But then as the acceleration level changes, as the acceleration level increases, if you sliced this with a plane, you would see that eventually they start to merge, and that's why we're ultimately getting 3. So if you took a horizontal slice, you'd be able to tell that. Now this is another way of looking at that same information, and this is a useful thing because it sort of, again, tells us something about the number of equilibria that we have. So on the bottom axis here, this guy is all the different orientations of the acceleration vector, from 0 to 359. On this guy is the acceleration levels, and everything in here is telling us, basically the colors are telling us how many equilibrium points we have at different combinations. So in the green, we've got 5 equilibrium points, which is the same as the ballistic. They're not in the same places. And below a certain level of acceleration, which we saw in the charts, we have 5 every time, no matter what the angle is of the acceleration vector. But as we go up, we see that we enter some yellow areas where there is 3. And when we looked at some specific alpha values, for example, we looked at 33, I enter this yellow region, so that's where I'm only going to have 3. Now surrounding this is a little purple line, which is indicating 4, but what that really indicates is just where the merge takes place. So that's where we have all of this information. Now, this is also useful for us actually when we're talking about trying to use this information for something. I promised that we'd look a little more closely near L1 and L2, and these are the 0 acceleration contours near that region. They look, they're pretty close to the ballistic case. Now this is another way to look at the same information. And what this is also, this is telling us something new though. So on the bottom line here, we again have all the alpha letters, alpha values, except 0 is now in the middle. So these are the negative values and these are the positive values. And rather than acceleration level, we're going to fix the acceleration level at our baseline, which is 7e minus 2. And this is our Hamiltonian, or our constant. And what this information is telling us is not only the number of equilibrium solutions that we have, but it's also going to tell us that when we can calculate, which we can also get 0 velocity curves and acceleration, of the forbidden regions. It's going to tell us what order that they open. Now, if you're familiar with the ballistic circular restricted problem, you know that as you change the energy level, you start with little ovals around the 2 primary masses. L1 opens first, L2 second, L3 third, and then 4 and 5, right? So this chart is telling me that that's not always going to happen in that particular order. But first things first, the one thing that I deduced from this particular line is if I took a particular angle and I started at this and draw this line up, this is telling me that I will cross these guys 5 times. So at an angle of 60 degrees, there are 5 equilibrium solutions. Over in this region, if I was at minus 140, in this particular case, I'm going to see 1, 2, 3, 4, 5. I'm also going to see 5 equilibrium solutions. But if I change this down to plus 40 degrees, I'm only going to get 3 equilibrium solutions. So I've got that information here. But the other thing is these lines. So these are different colors. And the reason for that is that the blue color tells me where L1 is. That's the interior libration point between the Earth and the Moon. The red one tells me where L2 is, which is on the far side of the Moon. And this guy tells me about E3. The important thing is when I've got alpha of 60 degrees here, as I start to move up, one of the things I see is that E2 opens first. So the first thing that happens when I have this value of low thrust, which is the non-dimensional value is 7e minus 2, I have an orientation of the acceleration vector of 60, that in that particular case, as I change the constant value, which is the Hamiltonian, as I change that, whoops, E2 will open first, then E1, and then I'm going to cross my 3 guys for the other 3 libration points. So that was not necessarily expected, but it's an interesting phenomena that we can go on to use to better understand what happens to the zero velocity curves. So given that information, what I'm looking at here is the ballistic case again. I have my 5 equilibrium solutions, and at a particular value of the Jacobi constant, this is what the zero velocity curves of the forbidden regions look like. So that should be familiar to folks who work in that particular problem. In this particular case, the gateway at 1 and the gateway at 2 is open, 3 is closed, and 4 and 5 are contained within the forbidden region. But now if I add low thrust acceleration, so I go back and I'm going to use the acceleration level of 7e minus 2, I'm going to use a thrust direction of 60 degrees. And the first thing I see is this value of the Hamiltonian over here. And I see everything, they're all closed, but it's not quite symmetric like it was in the ballistic problem. And here at this particular value of the Hamiltonian, or the low thrust constant, E2 has opened and E1 is still closed. Okay. And as I start increasing that energy value, I start to see my, remember alpha is 60 degrees, so I see the asymmetry, but I also see some other things opening in ways that I hadn't expected. And so eventually when I get up to minus 1.55, I've got what I see on the left, and I still have some equilibrium points in there, and then I disappear over here. There's an equilibrium point right in the middle there. So that was of interest, and that's going to tell me something, because when I look at these particular images, if I overlay these with some of the low thrust solutions that we've obtained with the appropriate assumptions, that's consistent with what we see. Now, talking about the stability was the next piece of information. And the different equilibrium points all have different stability characteristics. And when I'm looking at relatively low values of acceleration, it's probably a surprise to no one that the stability properties are similar to what they are in the ballistic case. So in that case, the definitions here are a saddle center and mixed meaning that we have complex with a real and imaginary part. And so on the left here, we're always going to have the ballistic case. And then for different images, we're going to have these guys. Now, they're colored. You can't see them very well here. But the saddles are red whenever you have an equilibrium point along those red arcs. Those are the saddle centers. Blue is center, and green is mixed. So these are all still pretty consistent. Over on the left, we've got ones that are really low level of acceleration, so their stability properties are the same as they were in the case where you were ballistic. This is a little bit larger, but I still see the blue and the red, which is pretty consistent. But now when I get to 7, e to the minus 2, which was my baseline, they're starting to change a little bit, and I'm starting to see some different stability characteristics. I see some green lines starting to enter and so on. The bottom line for that is that that's going to mean that there's different kind of behavior in those regions. More green, but a lot of different types of characteristics. That also means that I can look at other sorts of structures though. So I can look at some of these different characteristics, and even with my low thrust added, I can find periodic orbits in the center. I can find stable and unstable manifolds. I can get quasi-periodics and so on. But because of the different characteristics in different regions, I may be able to find different types of structures. This one looks very much like the ballistic case, the red and the blue being stable and unstable manifolds. But if I look a little closer, just at this particular image, these are stable and unstable manifolds for the equilibrium points themselves. On the left is our ballistic case, and on the right is our low thrust case for a particular value of acceleration and a particular orientation of the thrust vector. And what the takeaway is from this image is that because of all of these other types of properties, I have some manifolds now that may enter regions that they did not enter in the ballistic problem. So I may be able to flow into regions that I couldn't get into before, not surprising, but now I can actually see that there are some pathways into regions that I've been able to reach with manifolds in the past. So I can use that kind of information. So some examples of just, besides just understanding what's going on, what some simple examples of how I might use some of this information. I can take, for example, this is a collection of a lot of manifolds here, but if I wanted to get a transit, what I mean by that is I want to pass through L1 and L2 without any interference. These are some examples of one transit, which is green, and some non-transit orbits. For example, this guy goes to the other side, but then may get stuck in this particular orbit, which is a low thrust periodic orbit. There's only one transit guy here, but I could identify that one because that happens to be on our chart here for alpha equals 60 degrees, acceleration level at our baseline, and that's this particular point. Both L1, because I moved up here, I passed E2 and E1, so both of those are open, but 3 is closed, and that will give us an opportunity. It doesn't guarantee it, but it gives us an opportunity to transit, which is what we used in that previous problem. Just another example, I won't go through all the details, but in this particular case, what I might want to do is I might want to, for example, start at some location outside the system. I may want to enter the system, and in this particular case, maybe what I want to do is I want to get a strategy to enter the system and not pass through L1. So in this particular case, you can use these curves in order to design a control history that will put you on this path without any low thrust. It would naturally do that, but when you add low thrust, it closes the E1 gateway. This is the resulting path when you put the pieces together. And as a matter of fact, we can even get one that if we change then the acceleration level, we can close the L2 or the E2 gateway behind us and eventually turn off the thrust altogether for the resulting motion. So in this particular case with our simplified analysis, putting together a circular restricted 3-body low thrust model, we were able to make some reasonable assumptions which allowed us to do some analysis to produce low thrust equilibria, which gave us some different locations and gave us some other types of opportunities to reach different parts of the region. In this particular case, we used alpha and the Hamiltonian as constants, but we can then also follow up on those efforts and do some actual designs to achieve various results. So that's it. Yes?
Yeah, so thanks for the camera shot. This is going to be great. So I think.
Do you want to stand?
Yeah. Okay. Yeah. So this is not my area of expertise, but I always love hearing these talks, and so I'm about to ask something that is probably extremely stupid. So forgive me. It seems to me, my interpretation of what you showed, it's almost like a clever way to use low thrust to almost like synthetically create this fourth body that's coplanar to take advantage of that structure. It's almost because, given the constant acceleration, it's almost like having a fourth body that's fictitious at this angle alpha to take advantage of that, at least for a time being, to take advantage of these opening and closings. Is that maybe a...
To take advantage of them, because when, in the missions that they were working on, they would get optimized results. But unless you know what happened every step of the way, you don't know why did it produce that result. And if you had some better idea, which we're not necessarily done with the analysis, but if you had a better idea, they might not have to use like random starting assumptions in order to get somewhere, because it's very time intensive. Other questions? Yeah, Dan?
I just want to make sure I understand it. With your low thrust Hamiltonian, that's the constant that you get when you add the position dotted with the constant acceleration.
Yes.
Oh, okay. So for those, you have a fixed alpha, you don't change it, and then that gives you this additional structure.
Yes. You still have that R dotted with the acceleration, but then the Hamiltonian isn't constant.
Well, if the
low thrust Hamiltonian.
If the acceleration is constant, though,
yes.
that should be constant. Then
yes.
The whole Hamiltonian should be a constant.
Yes.
And
yes. Under that condition.
Or okay, and that's what you call H sub LT.
Yes.
Okay.
Under that assumption, that's right.
Okay. No,
okay.
It's very nice. Yeah, thanks.
Yes.
Thanks for your report or presentation. My question for you: if changes the dimension between the equilibrium point, symmetrical point, large or small, what better changes in your calculated method?
So in this particular case, we use, in order to get a non-dimensional set of equations, we use the distance between the Earth and the Moon as a characteristic length.
Mm-hmm.
Now, if I went to a different system where that was much longer,
yeah.
like the Sun, Earth, in order for my assumptions to remain valid, I would use a different type of set of characteristic quantities, which doesn't change anything about the physics, but it changes the size, the relative size of the quantities in the equation, so that the assumptions are still valid.
One more question. So there's been some, not the same, but similar work that people have done with solar sails, looking at balance points and all that. Has that been any help here, or is that just too different?
It's been a lot of help, actually. Okay, and they make a different set of assumptions to go through their process.
Right.
They have a harder time with some of the constants, but it's been very helpful to help set the problem up. Absolutely. In particular, some of the work that Ariadne Ferris did on the solar sail. Anybody else? Okay, thank you all.
Thank you so much, Professor Howell.